Hello, everybody. My name is Panagiotis. I am a student at the Mechanical Engineering Department of the University of Western Macedonia here in Greece. And today I am going to present a chaotic path planning system and coverage optimization using area segmentation. Starting off by the contents of this presentation, we're going to discuss about the motivation behind this work, the path planning system and the area segmentation. We will continue with the simulation results, then conclude this presentation and have some suggestions for future research. So I am sure that most of you are more than familiar with the chaos applications, which include communications, cryptography, and many more. And one of them is chaotic path planning, which itself has many modern day applications, such as floor cleaning devices, firefighting devices, surveillance of terrains, patrolling, and many more military applications. We chose from the literature the rainy map as a chaotic source, and we introduced an autonomous agent which has 8 possible directions and 8 possible orientations to move. The map generates numbers between 0 and 7, which represent each of the 8 possible movements and orientations. And as you can see, it produces a uniform distribution of these 8 numbers. And starting this work, we thought of letting the robot free to, with no restrictions to move. But we saw that the path was really sharp, and that made it really difficult to be applied to a real robot. So we thought of restricting the possible movements into 3: front left, and front right. So the robot doesn't make sharp corners and doesn't turn its orientation rapidly. And the thing that determines which are the 3 possible movements is the orientation. And as you can see in the left-hand side pictures, the orientation is 0. So the 3 possible movements are 7, 0, and 1. And on the other one, the orientation is 3. So the 3 possible movements are 2, 3, and 4. And the orientation itself changes according to the previous movement of the robot. So, for example, if the previous movement was 1, the orientation remains 1, and the 3 possible movements will be 0, 1, and 2. And if the previous movement was 2, the orientation of the robot changes to 2, and the 3 possible movements are 1, 2, and 3. Also, when the robot comes to a boundary, we applied some simple mirror mapping, and the robot stays where it is and changes its orientation to the opposite and continues its path normally. For the optimization of this technique, we thought of dividing the area into equal sub-areas. We introduced 100 by 100 area for the robot to cover. And we thought of dividing it into 4 and 16 equal sub-areas, which they have 2 and 3 different patterns respectively. Regarding the threshold of moving from one sub-area to another one, we considered 2 approaches. The first one, we gave the robot coverage target value to achieve. And when it is achieved, the robot can move from one sub-area to another. The evaluation parameter here is the number of steps needed to achieve the target value. And the other approach is giving the robot a certain amount of steps to perform. And the performance of the path was evaluated by the coverage itself. So as you can see, in the one whole area, all the steps are performed in the whole area. And in the 4 and 16 sub-areas case, a certain amount of steps are performed in each sub-area. So for the simulations, we introduced 2 more evaluation parameters, the mean visits and mean visits of visited cells, which can help us know the efficiency of the path. And also the simulations that are presented below regard the second approach of the threshold, which is giving the robot a certain amount of steps to perform and evaluating its performance by the coverage percentage. Also, one of the three patterns in the 16-area subcase and one of the two patterns in the 4-area subcase, in the 4 sub-area case, sorry, are presented because we saw that there is no difference between the different patterns in each case. We presented only one of its pattern. Here you can see the motion of the robot, which is really smooth. It visits almost the whole area, but we can see that there are some areas that remain unvisited or visited mildly, and some other areas that are visited multiple times. This is shown with the first simulation also, which we gave the robot 10,000 steps to perform. The coverage was about 59% and the mean visits visited about 1.67%. We can see that there are some areas that are visited 7 and 6 times and others that are not visited at all. And on the right-hand side graph, we can see that there are some areas that have very high coverage and others that have really smaller, about 40%. This is the same case with the second simulation and 20,000 steps. Here the coverage is about 82% and the mean visits visited about 2.42. We can see in the middle picture that there are some cells that are visited 10 and 11 times. And on the right-hand side picture, we can see that there are some areas that have a coverage of above 95% and some others that are below 65, which is a big deviation for the coverage in the whole area. This can be seen in this graph, which was derived from 50 simulations for this case. We can see the mean, the maximum and minimum coverage achieved in these simulations with the whole area. We can see that the difference between maximum and minimum is very big, and that's what we wanted to decrease to improve the system. So we divided, as I mentioned before, the area into 4 sub-areas having 2 different patterns, which, as I said before, there is no big difference between the 2 patterns, so one of them was examined. And the 16 sub-area robot, the 16 sub-area case, which it has 3 patterns, and likewise, there is no significant difference between the patterns. I present here the 2 first patterns in the 16 sub-area case. This is the first pattern and this is the second one. We can see that the motion remains smooth. And also by first sight, we can see that the whole area is visited and there are small areas that are unvisited and small areas that are visited more, but generally it is a uniform coverage of the whole area. Here in the first simulation, giving the robot 10,000 steps to perform, we can see that the coverage is about 63%, and the mean visits visited is about 1.59. When comparing it with one whole area where the coverage was about 59% and the mean visits visited about 1.67%, this is a big improvement. And also we can see that from the middle picture that there are some areas that are visited only 6 and 7 times, and there are some cells that are visited less than 1 time, but this is a small number. And also we can see in the right-hand side color graph that the coverage is uniformly distributed between the area. This case is true for the second simulation and the 20,000 steps. The coverage is about 86% now, whereas in the whole area and 20,000 steps was about 82%. We can see that this is a big improvement. Here we can see in the right-hand side picture that the coverage is also really uniform between the sub-areas of the whole area. Here we can see the same graph as before, but now for the 16 sub-area case. It was derived again by 50 simulations, and we can see that difference between maximum and minimum is really decreased. And also, if we compare the two curves together, we can see that the mean coverage is increased comparing it with one area. And mostly the deviation between minimum and maximum coverage is decreased, and it became a more consistent coverage achieving path. So to conclude this presentation, the system that is proposed had the chaotic behavior that was desired, and the path was highly unpredictable. The smooth path also made this idea applicable to a real robot, and using also the area segmentation for the optimization increased the mean coverage percentage, and also made the achieving of the coverage more consistent. And the coverage between the sub areas was more uniformly distributed. For future research, I think that using multiple optimization techniques to increase the percentage of the coverage is a nice way of continuing this idea. Also introducing obstacles in the area and between them, and also introduce some environmental unpredictability. I will make this idea applicable to a broader scope of applications where the environment is really unknown or it has obstacles. And finally, studying an experimental realization of the proposed idea to see whether it is applicable and what's the difference between theory and experiment. Here are the references, and I'm about finished now. I want to thank you very much for your attention, and see you in a bit in the questions section. Thank you.